Now we're going to talk about subdivision. So we've met this idea before. If you think back to when we were doing with covering spaces and the path lifting and homotopy lifting, to prove the path lifting theorem, we had to take a path and cut it up into lots of shorter paths. To prove the homotopy lifting theorem, we had to take a square and cut it up into lots of small squares. And same kind of thing is also useful in homology theory. But for this we're going to need to subdivide not just an interval or a square, but an arbitrary simplicial complex. So that's what we're going to do now. So here's a picture of a simplicial complex K. So in order to subdivide it, the first thing that we do is to introduce a new vertex on the middle of each edge. Okay, so here we've got an edge AC, and we put a point in the middle of that, so it's going to be called AC hat. Here we've got an edge from A to D, and we put a new point in the middle of there, that's going to be called AD hat. And so in terms of coordinates, of course, BD hat, for example, is just B plus D over 2. And then we also put a new vertex at the middle of each 2 simplex. So here we've got a 2 simplex ACD, and then ACD hat is in the middle there, so that's A plus C plus D divided by 3. And notice also we've renamed the vertices. I mean, a vertex A, for example, that just consists of that counts as a simplex on its own. And the middle of the simplex A is just A itself, so A hat is the same as A, B hat's the same as B, and so on. Okay, so now we need to connect up these new vertices that we've put in. And, so that's the kind of main content that we need to think about. There's some kind of combinatorial recipe for how the new vertices are connected together. We'll explain the general picture on the next slide, but here we just on this slide we just have a little preview. Okay, so here, for example, is one of our new 2 simplices with vertices D hat, BD hat, and ABD hat. And the reason why that kind of counts as a 2 simplex is like this, is because these are the centers of the simplex D, the simplex BD, the simplex ABD, and those simplices are nicely nested like this. D is contained in BD, contained in ABD, and whenever we have a situation like this, then we get a 2 simplex in the subdivision. Another example here, you've got a simplex vertices C hat, CD hat, and ACD hat, and the corresponding simplices in the original complex C, CD, ACD, they're nested in order like this, and so because of that we get a simplex C hat, CD hat, ACD hat in this subdivided complex here. So the general rule is like this. Given an abstract simplicial complex K, you're going to define a new complex, which is usually going to be called K prime or sometimes SPDK, as follows. As in the previous slide, for every simplex sigma of the original complex K, we get a vertex sigma hat of the new complex K prime. And then for every chain of simplices nested inside each other, sigma naught, sigma 1 up to sigma r of K, then these give us vertices sigma naught hat, sigma 1 hat up to sigma r hat of the new complex K prime. And in the situation where these simplices are nested, we declare that the corresponding new vertices form a simplex of K prime. Okay, so notice, I mean, although we've been kind of explaining this in terms of geometric pictures of which actually show the geometric realization of K, this formal definition here is really a definition with abstract simplicial complexes, just with these finite sets of vertices and simplices and so on. But so to explain how this kind of corresponds to the geometric pictures, we need to introduce this map called beta. So beta is going to be a map from the geometric realization of the new complex K prime to the geometric realization of the old complex K. And the way it works, if you've got a vertex of, if you've got a simplex of K, say sigma, then you get a vertex sigma hat of K prime. And we define beta of that sigma hat to be the center, to be V0 plus up to Vk divided by K plus 1. So that's a point in the geometric realization of K. Right? It's a formal linear combination of the vertices of K, in which all the coefficients are non-negative and add up to 1. And the set of vertices that have a positive coefficient, that has to be a simplex, but of course that's true here. I mean, the relevant set is just V0 up to Vk, which is our simplex sigma. Okay, so this guy here, this is called the barycenter of sigma. Okay, so that tells us what this map beta does on the vertices of K prime. But an arbitrary point in the geometric realization of K prime isn't just a vertex, it's some convex combination of vertices. It'll be some combination like this, sigma x sigma times sigma hat, where the x sigmas are non-negative real numbers adding up to 1. And in that situation, well, we just extend the definition of beta in the obvious way. Beta of this x is just the sum of the coefficients x sigma times these barycenters beta sigma hat. So, so beta is basically, I mean, in the case of the complex K that we were considering earlier, I mean, this is a picture of the realization of K prime. This is a picture of the realization of K. And beta sends this picture to that picture in the kind of obvious way. And we've drawn this in such a way that it's beta is more or less the identity. So it's a key point that this map beta is actually a homeomorphism. You see it here. I mean, this space here is just basically the same as that space. So, but we need to prove that in terms of the formal definitions. Okay, so let's consider a point y over here. So for beta to be a homeomorphism, in particular, it has to be surjective. We have to find some x here in the realization of K prime that gets mapped to this point y in K. Okay, so y we can express as some convex combination of vertices, T0, V0 up to TR, VR. So these coefficients, Ti as usual, they're non-negative and their sum is equal to 1. But we're going to choose to number the vertices as follows. We take V0 to be the vertex with the largest coefficient, then V1 to be the one with the next largest coefficient, and so on. So T1 is greater than or equal to so T0 greater than or equal to T1, greater than or equal to T2, etc. So they're in decreasing order. Okay. So now we're going to define sigma naught to just be the vertex V0 and S naught to be T0 minus T1. So notice that because these are in decreasing order, this S naught is greater than or equal to 0. And then sigma 1 consists of the first two vertices, and S1 is twice the difference, T1 minus T2. Again, because these are in decreasing order, T1 minus T2 is greater than or equal to 0, and so is S1. And then sigma 2 is V0, V1, V2. S2 is 3 times T2 minus T3. In general, sigma K consists of the first vertices V0 up to Vk. Sk is K plus 1 times the difference, Tk minus Tk plus 1. And we do this all the way up to case K equals R. So at K equals R, we've got sigma R is going to be V0 up to VR, which is the whole of the original simplex sigma. And SR is going to be R plus 1 times TR. Okay, so you sort of expect TR minus TR plus 1, but there is no TR plus 1. We've only goes as far as TR. You could just decide to define TR plus 1 equals 0, and then the pattern would continue, or we can just make an exception for this last case. Okay, but now, so as we mentioned already, because the T's are in decreasing order, it follows that the S's are non-negative. And we want to claim that the sum of the S's is equal to 1. So let's just see how that goes in the case where R is 4. So here's our S0 here, and this is our S1. This is our S2, this is our S3, and then this is our S4. Remember, there's a special thing for the last one because there is no T5. But notice here we've got a T1 here and a T1 here, T2 here, T2 here, T3 and T3, T4 and T4. So we collect everything together in the obvious sort of way. You've got a T0 in the beginning, and then you've got a plus 2 minus 1 T1, a plus 3 minus 2 T2, a plus 4 minus 3 T3, plus 5 minus 4 T4. So you just get T0 plus T1 plus T2 plus T3 plus T4. But we know the sum of the TI's is equal to 1 because we started with a point y that was in the geometric realization. So that's just equal to 1. Okay, so that was for the case R equals 4, but it should be very clear that it works in exactly the same way for any R. Okay, so here's where we were. We had a point y in the geometric realization of K, and we defined sigma K to be the simplex consisting of V0 to Vk. We define Sk to be K plus 1 times Tk minus Tk plus 1, and we've observed that these are non-negative and their sum is equal to 1. So that means that we can look at the sum of the Si sigma I hat. So notice here coefficients Si are non-negative, their sum is equal to 1, and it's kind of clear that the sigmas are nested, sigma naught contained in sigma 1, contained in sigma 2, etc. So by our definition of k prime, sigma naught hat up to sigma r hat that counts as a simplex of k prime, and so this y is actually an element of the geometric realization of k prime. And we want to claim that beta sends this to x. So again, we're just going to prove that in the case where r is equal to 4. Okay, so how does beta y look? So you've got s naught times sigma naught hat, which is just v naught, s1 times sigma 1 hat, which is v naught plus v1 over 2, s2 times sigma 2 hat, s3 times sigma 3 hat, s4 times sigma 4 hat. Remember, sigma 4 hat, you add up all the vertices of sigma 4 and divide by the number of vertices. Okay. But remember here that that we had this factor of k plus 1 here in the definition of sk, and that's going to cancel out this denominator. There's a factor of 2 in the definition of s1 to cancel that, factor of 3 in the definition of s2, factor of 4 in the definition of s3, etc. So what this ends up as is your s naught v naught is just this term here, or s1 v naught plus v1 over 2. You've got the factors of 2 which cancel, and then your s1 is t1 minus t2 multiplied by v0 plus v1. And then this term here, for example, that's t3 minus t4 times 4, and then divided by 4, and then multiplied by the sum of vertices. Okay. So again, we're going to rearrange this. Let's just take out the coefficient of v0 here. So you get a t0 minus t1 there, and then a t1 minus t2 times v0, a t2 times minus t3 times v0, t3 minus t4 times v0, t4 times v0 here. So we collect together all the coefficients of v0, and you see that they're mostly cancelling. Okay. And then let's look, say, at the coefficient of v2. We don't have any v2 here, we don't have any v2 here. We do have a v2 here, so you get a t2 minus t3 times v2, a t3 minus t4 times v2, and a t4 times v2, so that's all these things here. Again, they mostly cancel, the t3s cancel, the t4s cancel, I'm just left with a t2. So following through all that kind of cancellation, we just get t0 v0 plus t1 v1 plus t2 v2, t3 v3, t4 v4, and that's just equal to the original x. Okay, again, it works in exactly the same way if r is different from 4. So what we've shown here is that beta is surjective. For any point y and any point x in the realization of k, we've produced a point y such that beta of y is equal to x. So we're not going to go through the proof that beta is also injective, but I mean the point, what do we have to do to prove that beta is injective? Basically, we have to prove that we didn't really have any choice about what these s's and sigmas were. Okay, so you can just more or less work back through the same steps to show that there wasn't any choice, and so yeah, beta is also injective. So that means it's a bijection from the space mod k prime to the space mod k, and mod k prime is compact, and mod k is Hausdorff, and we had this basic theorem that continuous bijection from a compact space to a Hausdorff space is the inverse is automatically also continuous, and so the maps are homeomorphism.